The global water crisis. Currently, 1 in 10 people don't have access to clean water. This means 663 million people are without safe drinking water. The main victims of the global water crisis are women and children. In fact, in the time it takes to fill a glass of water, just 21 seconds, a child dies from a waterborne illness. Not only will water scarcity impact the health of individuals, it can also lead to food scarcity, as water is needed to irrigate farmland. It can also potentially result in international conflict, as countries compete for access to clean water. So how can we solve the global water crisis? 71% of the world is made up of water. The ocean holds 97.5% of all Earth's water. Using proper separation techniques, this untapped resource can be used to obtain clean drinking water. Current water separation techniques to do this are forward and reverse osmosis technologies. Let's briefly discuss what osmosis is. Osmosis is the phenomenon of water moving across a semi-permeable membrane to an area of higher solute concentration in an attempt to equalize concentration within the system. A key component to forward and reverse osmosis is the membrane. A membrane is a thin selective barrier that will let some molecules cross while rejecting others. Let's take a look at reverse osmosis. Reverse osmosis filters salt water through a selectively permeable membrane in order to obtain pure water. As the concentrated feed, shown on the left, is pressurized, water will cross the membrane. Forward osmosis is driven by a difference in osmotic pressure. A selectively permeable membrane, shown in gray, separates the feed on the left and the draw solution on the right. Due to the solution's increased concentration, it has a greater osmotic pressure. In order to equalize this pressure, water molecules will permeate the membrane towards the draw solution. The experimental objective. In the reverse osmosis experiment, you will be testing two things. First, the effects of pressure on the SW30 and BW30 membranes. The second, you will be comparing the two membranes' salt rejection. In the forward osmosis experiment, you will be determining the effects of pressure on a pressure-retarded and forward osmosis membrane. The graph in the upper right corner displays the concentration profiles of a forward osmosis system. You will need to calculate 4 separate concentrations to determine the permeability of each membrane. The graph in the upper right corner shows the concentration profiles of a reverse osmosis system. In the animation, the blue arrows display the continuous flow of water through the membrane. The concentration has the greatest at the membrane wall as it traps the salt from the bulk being fed in.
This is the reverse osmosis setup. Set the chiller to 19.6 degrees Celsius and make sure the water level is between the maximum and minimum lines. Make sure the drain valve is closed and that the bypass valve is open. Fill the feed with 9 liters of distilled water. Fill each cell with a small amount of DI water. Load the membranes into each cell. For this process, the shiny side of the membrane should be facing downward. Place the top on the cell. Use a wrench to screw the cell together in a star pattern. Turn on the pump. Set the pressure and flow rate using the 2 gauges. The silver needle valve sets the pressure and the green needle valve sets the flow rate. These will need to be adjusted simultaneously to get the desired pressure and flow rate. If bubbles form in the tubes, simply hold the tube straight up and tap gently. Allow the membranes to equilibrate for 20 to 30 minutes. Weigh 3 empty graduated cylinders. Place permeate tubes in graduated cylinders and simultaneously start a timer. Collect enough permeate to cover both metal bands on the conductivity probe. This is about 11 milliliters and should take 10 to 20 minutes. Reweigh the cylinders and then pour the liquid back into the feed. Repeat to obtain a second data point at this pressure. Change the pressure and repeat the testing process. Do this for all desired pressures. Dissolve 29 grams of NaCl in 1 liter of water. Measure the conductivity of this solution and the feed, then add to the feed. Allow feed to mix for 10 minutes and then record feed conductivity again. Perform same collection procedure as pure water test, but measure the conductivity of each sample. Make sure that both metal bands are covered by the liquid. Rinse the conductivity probe in between readings with DI water. Change the pressure and repeat testing process. Do this for all desired pressures, obtaining 2 data points for each pressure. Turn off the pump and the chiller. Drain the feed tank into a bucket. Be sure to close the valve before any air enters the pump. Refill the tank with 10 liters of tap water. Detach the return lines and place them in a bucket. Turn on the pump and flush the system. Stop before any air enters the pump. Repeat with another 10 liters of tap water and then 10 liters of DI water. Reconnect return lines. Close the bypass valve. Air purge the system with a compressed air line.
Do not completely connect the fittings.
Reopen the bypass valve. Unscrew the cells. Remove the membranes and inspect for defects.
Dispose of the membranes and leave the cells open to dry.
This is the forward osmosis setup. Turn on the chiller and set to 19.3 degrees Celsius. Make sure the water level is between the lines. Fill the feed and draw tanks with 2 liters of DI water each.
Place the draw tank on the scale and the feed tank on the stir plate.
The membrane needs to be cut so that it does not touch the outer ring, but covers the inner ring. The membrane should be placed with the dark side down. This is what the membrane should look like in the cell. Place the top on the cell and put washers and screws over the top. Use a wrench to screw the cell together in a star pattern. Start the data acquisition software. Click New Data Log and name your file. Click Open and then Start Data Log. Check that all connections are secured on the tanks and the cell. Turn on the pumps and set the flow rate using the knobs on the pumps. You can see what flow rate it is by the yellow rotometers. Set the pressure with the knobs underneath the rotometers. The pressure and flow rate need to be set simultaneously. Allow system to equilibrate until the change in draw solution mass is less than 0.05 grams per minute. Add the volume of 5 molar NaCl that will bring the draw solution to the first desired concentration. Record both the feed conductivity and temperature. Collect data for 30 minutes, then add 5 molar NaCl to the draw tank for the next concentration. Repeat for 4 concentrations total. Turn off the pumps and stop data collection. Empty both tanks into the sink and fill with 2 liters of tap water each. Reconnect the tanks and flush the system for 5 minutes. Repeat again with tap water and then with DI water. Purge the system with compressed air.
Do not completely connect the fittings.
Remove the membranes and inspect for defects.
Dispose of the membrane and leave the cell open to dry.
Here are some useful calculation tips for analyzing the data. The calibration curve will give an equation of the line in the format y equals mx plus b. The b value should actually be 0, but it is not due to the lack of accuracy with the conductivity probes. For this reason, only use the slope of the calibration curve and disregard the b value. When calculating the Reynolds number, make sure you use hydraulic diameter. In our case, the height is 1 inch and the width is 1/8 inch. These values are the membrane channel dimensions through which the water flows. The calculated Reynolds number should be in the upper laminar or the transition range. In order to find the volumetric flow rate, the mass of the sample must be known. Finding the mass can be a bit tricky. Make sure that you take the mass right before adding more sodium chloride to the draw feed, minus the mass where the other sodium chloride solution was poured. To find the permeability of the salt for forward osmosis, plot the flux versus the change in effective concentration. Then the equation of the line will give you how to determine your B value. Again, as in the calibration curve, only use the slope of the graph. The experimental findings concluded for a reverse osmosis system that as pressure decreased, salt rejection increased, and for both the forward and reverse osmosis system, as pressure increased, water flux increased.